Welcome to Space Dreams documentary, where dying stars approach oblivion and matter struggles to remain itself. Between neutron stars and black holes lies a pause, where collapse slows and verdict remains unfinished. A ruined core does not fall cleanly because matter keeps resisting after everything else is gone. A neutron star survives only provisionally its apparent stability, bought by pressures forever nearing failure. The mystery is not collapse alone, but why gravity pauses after erasing atoms, electrons and matter. Here, matter obeys harsher laws, with distorted nuclei and crowded particles bending substance beyond human intuition. Density is not enough. Relativity, pressure, mass, and structure decide whether collapse still meets resistance. So the border is not a line in space, but a negotiation written inside matter. The losing point seems fixed, yet spin heat composition and hidden physics keep moving it deeper inside. Neutron star stops being an adequate name, as stranger phases begin replacing familiar substance. Some remnants delay defeat with rotation heat and merger violence, briefly holding collapse above the abyss. In that suspended interval time, itself seems to thicken, letting astronomy witness a nearly lost argument. When neutron stars collide, the borderland broadcasts gravitational waves, heavy elements, and brief electromagnetic confession. Gold and platinum emerge from this violence, making human treasure a residue of almost failed stars. A black hole is not merely heavier. Beyond the threshold, matter loses every way to persist. To understand that crossing, we must read aftermaths, because the decisive interior remains almost unreachable. Pulsars, X-ray timing mergers, and gravitational waves let the universe measure how dense matter may remain. Even survival bleeds as crusts break, spins slow, and magnetic fields erupt from negotiated stability. Yet the decisive physics hides deepest, leaving us fragments, signatures, and aftermaths instead of direct sight. Here, the universe judges matter itself, deciding whether structure, memory, and resistance may continue at all. What stands at this border is not only an object, but reality testing its final terms. Like, subscribe, and thank you for listening as we enter the first hesitation of collapse. A neutron star is what remains when a star both dies and refuses to disappear. That is the first contradiction. The surface story says, collapse ends the matter cleanly. A massive star runs out of fuel, its core fails, gravity wins, and a black hole waits on the other side. But the real story is stranger, because there is a borderland where gravity does not yet get total victory, and matter does not yet surrender its right to structure. In that borderland, a dead star becomes one of the most extreme objects in the universe. An object so dense that the old language of solids, gases, atoms, and nuclei begins to break. A neutron star is not simply a small star. It is not a burned-out ember. It is matter after defeat, compressed so violently that the familiar architecture of the world has been stripped away almost entirely, yet not completely. And that last distinction is the whole mystery. Because if the compression goes only a little further, the object is no longer a neutron star at all. It becomes a black hole, and the story changes from one kind of existence to another. From a distance, the difference can seem almost trivial. Both neutron stars and black holes are born from stellar catastrophe. Both mark the point where ordinary fusion, the long-burning engine that lets stars resist their own weight, can no longer hold the center up. But this only looks simple from a distance. The real problem is not that stars die. The real problem is what happens after death has already begun. In the final life of a massive star, fusion climbs a steep ladder of elements until the core builds iron, which offers no further profit. Iron is the end of the bargain. It will not release energy the way lighter elements do. So the outward pressure that once pushed against gravity collapses almost at once, and the center of the star begins to fall inward under a weight it has been delaying for its entire existence. First comes the inward disaster. That collapse is not gentle. Electrons are forced into protons. Atoms lose not just their shape, but their identity. The vast empty spaces that make ordinary matter mostly nothing are crushed out of existence. The core shrinks fast. An object with a mass greater than the sun is squeezed toward the size of a city. To say it becomes dense is true, but too mild. Density here is not a number on a chart. It is a regime change. A teaspoon of this material would outweigh mountains. Light itself struggles to leave. Time near the surface runs under stronger gravity than almost anywhere else outside a black hole. And still, even here, gravity has not finished its work. The collapse does not always continue all the way. Sometimes something pushes back. At first, this sounds like a technical detail. It is not. It is the central drama. A neutron star exists because, under conditions that should seem unsurvivable, nature finds one more form of resistance. Not chemical resistance, not the rigidity of rock or metal. Those concepts are long gone. What remains is pressure at the level of quantum matter, a refusal built into particles themselves, amplified by forces that only become visible when the universe is driven into a corner. This is why a neutron star is so unsettling. It is not just heavy. It is an object balanced on laws deeper than the ones that govern everyday experience. It survives because matter can still oppose compression, but only barely and only under terms alien to ordinary life. The achievement is real. The cost is larger. To create a neutron star, a star must be destroyed so completely that almost every comfortable category of matter is erased, and yet one thin possibility remains: not enough resistance to stay normal, but just enough to avoid the abyss. This is where the borderland begins to matter. A black hole is what happens when compression stops being a state of matter and becomes a trap in space-time itself. A neutron star is what happens when matter still manages somehow to exist as matter under pressures that nearly forbid the fact. That means every neutron star is a narrow escape, every one a verdict delayed, every one a reminder that collapse is not a single event, but a negotiation. The obvious explanation is that gravity crushes and pressure resists. The real explanation is that the identity of the object depends on how far that contest can go before matter loses the right to remain organized. And this is why neutron stars are more than compact leftovers from stellar death. They are physical border posts. They tell us there is a limit somewhere between survivable structure and total gravitational defeat. Yet they also tell us that we do not know that limit cleanly. Some spin hundreds of times each second, as if motion itself is helping them postpone judgment. Some carry magnetic fields so violent they can tear at their own crusts and flood space with radiation. Others are locked in binaries, circling another dense remnant as they lose energy and move toward collision. In every case, the same question waits underneath: how much weight can matter bear, before it is no longer matter in any recognizable sense. Not how much weight a star can hold. How much reality can be compressed before reality changes category. That is the deeper hook beneath the spectacle. The story on the surface is about dead stars. The story underneath is about the last defensible form of matter before disappearance. Somewhere inside these objects, physics is pushed close to its breaking point. Somewhere inside them, the distinction between a neutron star and a black hole is being written in pressure density relativity and forms of matter that may barely resemble the names we give them. So before this story can become one of collisions, heavy elements, pulses, or gravitational waves, it has to answer a harder question. What hidden arrangement of matter can stop a collapsing star at the edge of oblivion and hold it there even temporarily? Because until that answer becomes clear, a neutron star is not really an explanation. It is a pause. And pauses this extreme never come for free. A neutron star looks finished. That is the illusion. It seems to be the cold conclusion of a stellar catastrophe, a compact survivor left behind after the explosion has already said everything worth saying. But a neutron star is not the end of the event. It is the event still happening in slower motion. The star has died, yet the core has not reached peace. It has only reached a form of endurance so extreme that stability becomes misleading language. What appears from far away to be a permanent object is in truth a truce written under impossible pressure. The surface may harden, the spin may regularize, the pulses may arrive with astonishing precision. But none of that means the deeper crisis is over. A neutron star survives because collapse has been halted, not because collapse has been resolved. That difference matters. In ordinary life, survival suggests safety. Here, it means the opposite. It means gravity has been stopped at the last defensible line and is waiting to see whether that line holds. Consider what this object has already endured. A stellar core more massive than the Sun has been crushed from something the size of a world into something scarcely wider than a city. The inward force is so severe that the old emptiness of atoms, the generous distances that make rocks, oceans, bodies, and planets possible, has been almost entirely erased. Matter has been packed until atomic identity itself becomes secondary to compression. And the result is not a calm sphere resting comfortably in space. It is a body with surface gravity hundreds of billions of times stronger than Earth's, a body whose crust may be only about a kilometer thick. Above deeper layers of matter, we do not fully understand a body that often spins with absurd speed, because the collapse that made it also wound it tight. A child's toy skater pulling in her arms is enough to suggest the principle. But the scale here is merciless. A core that once rotated modestly can become an object spinning dozens, hundreds, even in some cases more than 700 times each second. This is not decorative motion. Rotation helps support the star. It redistributes the burden. It buys time. And that reveals the deeper truth already hiding inside the object. Even after formation, a neutron star may still be relying on temporary advantages. Temperature matters. Rotation matters. Magnetic structure matters. Composition matters. The obvious explanation is that a neutron star exists because neutron pressure stops gravity. The real explanation is harsher. A neutron star exists because several forms of resistance combine for a while, and some of them weaken. Heat radiates away. Rotation slows. Magnetic fields twist decay and sometimes explode outward through the crust in violent rearrangements. Matter can fall back from the original supernova, or later be stolen from a companion star if the neutron star lives in a binary system, adding new weight to an already stressed remnant. Each of these changes alters the terms of survival. So, a neutron star is not merely a dense object. It is a living ledger of pressures and losses. Even its famous regularity can conceal fragility. Pulsars seem almost supernatural in their precision, flashing beams with a timing that can rival atomic clocks. Yet those clocks can glitch. Their crust may crack. Their interior superfluids may shift angular momentum, suddenly producing tiny jumps in spin that reveal stress buried deep inside. Magnetars, the most violently magnetized members of the family, look even less secure. Their fields can be so intense that the crust itself strains beneath them. When that strain gives way, the star can release bursts of energy powerful enough to rattle space across the galaxy. These are not signs of serene existence. They are signs of an object paying ongoing costs for having survived at all. And the cost is not merely local. Every neutron star also carries a larger sentence over its existence. There is a mass range within which matter can still hold the line, and beyond which it cannot. But nature does not paint that boundary in bright ink. It allows objects to approach it from different directions. A neutron star may be born light enough to endure, then pushed closer to danger by accretion. It may be born spinning so fast that rotation helps hold it up, only to drift toward collapse as the spin bleeds away. It may emerge from a merger grotesquely overmassive, and survive only for milliseconds or seconds because heat and rotation delay the inevitable. From far away, these all look like the same kind of remnant. From the inside, they are different negotiations with the same judge. That is what makes the borderland so compelling. A neutron star is not defined only by what it is. It is defined by what it has not yet become. This is why the phrase stable neutron star must be used with care. Yes, some may survive longer than the current age of the universe. But longevity is not the same as simplicity. A mountain may last. A neutron star endures by balancing on microphysics relativity and a hidden internal structure we still cannot directly inspect. Its victory may be long, but it is never casual. It is purchased second by second. And once that becomes clear, the object changes meaning. It is no longer just the remnant of a supernova. It becomes a threshold object, a thing whose existence tells us that gravity can be resisted farther than intuition allows, but not infinitely. Somewhere inside matter is doing something extraordinary to keep the star from vanishing into a black hole. Somewhere inside, the last useful form of pressure is holding. The natural question is no longer why neutron stars exist. The natural question is what exactly is doing the holding, and why gravity stops here at all when it has already destroyed almost everything else. Gravity does not need to destroy a star all at once. It only needs to find the point where resistance fails faster than new resistance can form. That is the deeper logic of collapse, and it changes how a neutron star must be understood. The easy version of the story says the core falls inward until neutrons push back. But that is only the surface model. The real problem is more severe. By the time a neutron star is born, gravity has already defeated most of the known forms of structure. It has overwhelmed thermal pressure from fusion. It has erased the spacious geometry of atoms. It has forced electrons and protons into closer and harsher arrangements than ordinary matter can tolerate. So why does the process not simply continue without interruption into a black hole? Why does gravity, after proving so overwhelming, pause at all? The answer is not that gravity becomes weaker. It is that gravity runs into a new kind of opposition, one that does not come from chemistry heat or the familiar rigidity of material things, but from the rules that govern matter at its deepest crowded limit. To see why that matters, it helps to strip away the image of a neutron star as a hard ball in space and think instead of a collapsing argument between compression and identity. In ordinary matter, particles have room. Atoms are mostly emptiness, and that emptiness is what makes tables, solid air breathable and worlds habitable. But when a massive stellar core collapses, that room disappears. Electrons are squeezed into nuclei. Protons and electrons combine into neutrons. The old arrangement of matter is not compressed politely. It is abolished. At that point, what remains is an enormous mass of particles packed to densities comparable to atomic nuclei, a state so unnatural to daily experience that even the word solid becomes misleading. Yet something still resists further collapse. Part of that resistance comes from a quantum rule that seems abstract until everything depends on it. Identical fermions cannot all occupy the same quantum state. Neutrons belong to that family. They cannot simply pile into the same conditions without limit. As more of them are packed together, they are forced into higher and higher momentum states, creating a pressure that is not powered by heat and does not require fusion. This is degeneracy pressure, and it is one of the strange quiet laws that become decisive only when the universe is pushed into brutality. But even that is not the whole story. The obvious explanation is that degeneracy pressure saves the neutron star. The real explanation is that degeneracy pressure is only one part of a layered defense. At these densities, the strong nuclear force also matters because nucleons do not merely coexist like marbles in a box. They interact. They repel each other at very short distances. The details of that repulsion, the behavior of matter under extreme compression, and the exact relation between pressure and density all become part of a hidden rulebook called the equation of state. And this is where the story becomes more unsettling, because the survival of a neutron star depends on a rulebook humanity still does not fully know. We know such stars exist. We know some of their masses. We can infer some of their radii. We can watch their spins, their magnetic violence, their collisions, their gravitational wave signatures. But the central question remains partly concealed: what exact arrangement of dense matter gives enough pressure at enough depth to keep gravity from driving the core over the edge? This uncertainty is not a side note. It is the borderland itself. Because if the equation of state is stiff, meaning pressure rises sharply as matter is compressed, then neutron stars can support greater masses before collapse. If it is soft, they fail sooner. A difference in microphysics becomes the difference between an object that survives and an object that vanishes behind an event horizon. And gravity is merciless in how it exploits weakness. Add enough mass and even neutron degeneracy is not enough. Reduce rotational support and an object that once endured may no longer do so. Alter the internal composition and the balance may shift again. This is why the threshold between neutron star and black hole cannot be treated as a simple label. It is a stress test of matter itself. Somewhere inside the core, pressure must rise fast enough to answer gravity at every new increment of compression. If it does not collapse, resumes. The star loses its final argument. What makes this especially profound is that the contest is not being fought in the familiar language of objects, but in the language of allowable states. A neutron star survives because matter is still permitted under certain conditions to occupy configurations that preserve structure. A black hole forms when no such configuration remains accessible. That means the crucial battlefield is invisible. It lies beneath the crust, beneath the magnetic field, beneath the beams, and bursts and measured pulses in a domain where density approaches the limits of known nuclear theory, and where the identity of matter may already be changing. So when astronomers weigh neutron stars, or constrain their radii with X-ray observations and merger signals, they are not merely cataloguing exotic remnants. They are interrogating nature at the exact point where gravity tries to erase the distinction between matter and collapse. A neutron star, then, is not simply a dead core. It is the place where gravity finds the weak point in ordinary matter, breaks through it, and then meets a deeper resistance that may or may not hold. And that leaves us with a harder question than the one we began with. If matter can resist collapse this far, what does matter become in order to do it? Inside a neutron star, matter is not merely compressed, it is rewritten. That is the point where familiar language begins to fail. People often imagine extreme density as ordinary material packed tighter and tighter, as though a neutron star were just a larger amount of known substance forced into a smaller space. But the real transformation is more radical than that. At these pressures, matter does not simply become denser. It begins to occupy forms that have no true counterpart in the everyday universe. The story on the surface is about a dead stellar core. The story underneath is about the breakdown of ordinary categories. Solid and liquid no longer mean what they mean on Earth. Atom and nucleus no longer mean what they mean in a laboratory. Even the idea of a particle as a stable little object becomes less secure the deeper one goes. A neutron star survives because matter can still organize itself under enormous stress. But the cost of that survival is that matter must become stranger, harsher, and less intuitive at every layer. Start at the outside, where the conditions are already beyond anything human engineering could ever create. The crust is often described as solid, and in one narrow sense that is true. It is a rigid outer shell, a lattice of nuclei embedded in a sea of electrons. But even this most familiar region is familiar only by comparison with what lies below. The gravity is so strong and the compression so relentless that the nuclei are packed together in ways impossible in normal matter. Descend deeper, and the nuclei grow more neutron-rich as electrons are driven into protons. What exists here is not ordinary metal, not rock, not anything we can hold or melt or fracture in the normal sense. It is a crystal under apocalypse matter, organized only because it is being crushed hard enough to prohibit softer arrangements. And then the deeper distortion begins. As density rises toward the base of the crust, nuclei are forced so close together that the neat spherical shapes found in textbooks become energetically unfavorable. This is one of the most revealing details in the entire story, because it shows that the borderland is not just about stronger gravity. It is about matter abandoning the shapes it prefers under gentler conditions. Under pressure, intense enough, nuclei may stretch into rods, flatten into slabs, twist into tunnels, and layered forms that physicists with a touch of dark humor have named nuclear pasta. The terms sound playful. The reality is not. These shapes may be among the strongest forms of matter in the universe, not because they are elegant, but because they are what remains when gravity drives ordinary structure almost to destruction without fully erasing it. This is the deeper pattern of the neutron star. Every layer is an adaptation to conditions that should have abolished structure entirely. Beneath the crust, the uncertainty becomes more severe. The obvious explanation is that the interior is simply made of neutrons packed together in bulk. The real explanation is that nobody is fully sure what matter does when it is squeezed beyond nuclear density and held there by gravity rivaling the edge of black hole formation. There may be superfluid neutrons moving with almost no viscosity, allowing angular momentum to shift in sudden jumps that we observe as glitches in pulsars. There may be superconducting protons threading the interior with magnetic complexity. There may be hyperons particles containing strange quarks appearing when the pressure becomes high enough to make their existence favorable. There may even be a transition so deep that neutrons and protons lose their separate identities and dissolve into deconfined quark matter, a state more like a continuous sea of fundamental constituents than a collection of familiar nuclear particles. This is where the subject stops behaving like an extension of known astrophysics and starts approaching a confrontation with the limits of nuclear theory itself. Because the deeper one goes, the less clear it becomes what counts as matter holding together. And that uncertainty is not an inconvenience. It is the main event. A neutron star is a real object supported by pressure, but the source of that support depends on how matter responds when every easier option has been stripped away. If new particles appear, they may redistribute energy and soften the equation of state, making the star easier to compress. If quark matter forms, it may either weaken the resistance or, under some conditions, create a new way of bearing weight. If superfluidity dominates, it changes how heat, rotation, and stress move through the star. Each possibility alters the terms of survival. Each possibility changes where the border lies between neutron star and black hole. This is why the inside matters more than the spectacle outside. Pulses, bursts, and merger signals are dramatic, but they are surface clues to a deeper constitutional question: what forms of matter are physically allowed when gravity compresses substance beyond the point where atoms, nuclei, and common intuition remain reliable guides? That question carries a larger consequence. Because if the survival of a neutron star depends on these hidden internal states, then mass alone cannot tell the whole story. Two objects of similar size may endure differently, depending on what matter has become inside them. The answer seems clear until the structure becomes visible. A neutron star is not just heavy. It is internally negotiated. Its crust core and microphysics all participate in the verdict. And once that is understood, the next layer of the mystery becomes unavoidable. If matter changes this much under pressure, then the difference between a neutron star and a black hole cannot be explained by density alone. The real boundary depends on something deeper, not merely how much mass is present, but how that mass is arranged, what pressures it can generate, and whether those pressures rise fast enough to answer gravity before matter runs out of possible forms. People often imagine the difference between a neutron star and a black hole as a matter of simple quantity. Add enough mass, squeeze hard enough, cross a line, and the object changes category. That sounds reasonable. It is also incomplete. The easy explanation is that black holes are just denser. The real explanation is more difficult because density by itself does not decide the outcome. A neutron star can be denser than some other compact object and still not be a black hole. A black hole is not defined by having a lot of density in some vague sense. It is defined by a deeper failure, the failure of any physically allowed internal structure to hold the mass up outside its own event horizon. That means the crucial issue is not how crushed the matter looks from the outside, but whether pressure can still build quickly enough, deeply enough, and in the right relation to gravity to preserve a surface at all. Once that becomes clear, the borderland stops looking like a simple staircase and starts looking like a trap built into space-time. In ordinary intuition, pressure is a saving force. A gas pushes outward. A solid resists being compressed. Heat inflates. Compression meets resistance, and resistance buys stability. This remains partly true in neutron stars, but only partly. General relativity changes the terms. In Einstein's gravity, Pressure does not merely oppose collapse. Pressure also contributes to the gravitational field. That is one of the least intuitive facts in the whole story, and one of the most important. The very thing that helps support the star also adds to the burden the star must support. The object is not simply fighting gravity with pressure. It is using pressure in a regime where pressure itself becomes part of gravity's bookkeeping. This is why the obvious explanation fails. You cannot understand the neutron star black hole boundary by picturing an increasingly heavy ball held up by an increasingly strong spring. The spring becomes heavier as it stiffens. The defense feeds the threat, and the closer the object comes to the limit, the more severe that paradox becomes. This is also why radius matters almost as much as mass. A black hole is not just what happens when an object becomes very heavy. It is what happens when enough mass is compressed within a small enough region that escape in the relativistic sense ceases to be available even to light. A neutron star can sit terrifyingly close to this condition. Light leaving its surface is red-shifted. Time runs measurably slower there than far away. Space-time is so curved that part of the far side can be brought into view, making the star appear visually larger than its true geometric size. Yet, even under these conditions, there is still a surface. There is still an outside from which radiation can escape. There is still matter arranged in a star, rather than hidden behind a horizon. The existence of that surface is the whole difference. It means pressure is still winning, barely at every layer that counts. But barely is the word that matters. Because as mass rises, the pressure required to support the star rises too. That extra pressure strengthens gravity. The stronger gravity demands still more pressure. The star is driven into a vicious circle. To survive, matter must become more resistant. But each increase in resistance comes at relativistic cost. The story on the surface is about support. The story underneath is about a feedback loop, and that loop has an end. This is where the famous mass limit enters the conversation, though even here the simple version misleads. People want a clean number. They want a sharp threshold like a posted sign below this neutron star, above this black hole. Nature is less cooperative. There is indeed an upper mass beyond which no non-rotating neutron star can remain stable, a limit usually associated with Tolman, Oppenheimer, and Volkoff. But that limit is not just a single universal number handed down independently of microphysics. It depends on the equation of state, on how compressible dense matter really is, on whether exotic particles appear, on whether the core softens or stiffens, on whether rotation is lending support, on whether the object is still hot from birth or merger, and on how close it already stands to runaway collapse. The number exists, but it is not simple. It is the visible edge of hidden physics. This matters because two objects with nearly the same mass may not share the same fate. One may survive if its internal matter generates pressure efficiently enough. Another may collapse if its composition allows less support. One may persist because rapid spin spreads the load and deforms the star away from perfect spherical compression. Another may fail after it spins down and loses that advantage. One may be temporarily upheld after a merger by heat and differential rotation, only to disappear into a black hole once those supports bleed away. The answer seems clear until the structure becomes visible. What matters is not the mass alone, but the relationship between mass-radius pressure and the kinds of matter nature still permits under extreme compression. A neutron star is therefore not the last step before a black hole in some neat visual sequence. It is a conditional state. It exists only because the interior can produce enough pressure in a small enough radius under relativistic gravity without triggering the exact conditions that abolish the surface altogether. A black hole is what happens when no such configuration remains. The transition is not merely from more dense to most dense. It is from a world where matter can still define the object to a world where geometry does. That is the deeper fracture in the story. A neutron star is still made meaningful by its interior. A black hole is defined by the loss of any accessible interior structure that can communicate outward. So the real question is no longer whether there is a limit. The real question is why that limit shifts what hidden properties move it, and why nature refuses to draw it with a single clean line. The universe does not post a clean sign at the edge of neutron star survival. That is what makes the boundary so difficult and so revealing. People often ask for the maximum mass of a neutron star as though nature were keeping a simple ledger below one number matter survives. Above it, gravity wins. But the real boundary is less like a wall and more like a frontier that shifts with hidden conditions. There is a limit? Yes. There has to be. A neutron star cannot keep adding mass forever while remaining a neutron star, because pressure can only rise so far before the same physics that supports the object is no longer enough to hold space-time open around it. But the real problem is not whether a limit exists. The real problem is that the limit depends on what the star is made, of how fast it spins, how hot it is, how recently it was born or merged, and how matter behaves in a regime we still cannot reproduce directly on Earth. So the borderland is not marked by one simple number. It is marked by a moving verdict. The famous theoretical threshold for a non-rotating neutron star, the Tolman-Oppenheimer-Volkoff limit, is often treated as the final answer. In truth, it is the beginning of the harder question. That limit describes the greatest mass a perfectly cold non-rotating neutron star can support for a given equation of state. Even that phrase hides a great deal. Perfectly cold does not mean cold in the everyday sense. It means cold enough that thermal pressure is not a major source of support. Non-rotating means stripped of one of the most important temporary defenses a real neutron star can possess. And for a given equation of state means that the answer changes if dense matter changes. The obvious explanation is that the maximum mass is a property of gravity alone. The real explanation is that it is a property of gravity interrogating matter under impossible conditions. If matter is stiff, pressure rises sharply as density rises, and the star can hold more mass. If matter is soft, the support comes too slowly and collapse arrives earlier. A small difference in microphysics becomes a large difference in fate. Rotation complicates the picture even further. A spinning neutron star is not just moving for dramatic effect. Spin redistributes support, lowering the effective burden in some regions, and allowing the star to bear more mass than it could if it were standing still. This can matter immensely. A rapidly rotating neutron star may survive above the usual non-rotating limit for a long time, especially if it was born fast or spun up by stealing matter from a companion. But spin is not a permanent gift. Rotating stars radiate. Magnetic torques slow them. Pulsars lose energy. As the spin declines, the extra support declines with it. This means a neutron star can be alive on borrowed mechanics. It can spend years, centuries, or far longer existing in a state that is only possible because motion is helping matter endure. And once the spin falls below what the mass requires, the object may cross the border, not because new weight arrived, but because an old advantage disappeared. That alone should change how the threshold is imagined. The line is not just about mass. It is about support history. Heat introduces another distortion. A newly born neutron star, or the hot remnant, produced in a neutron star merger, can temporarily endure more than a colder object because thermal pressure and differential rotation may help hold the core up. But this survival is fragile from the start. Heat leaks away through neutrinos and radiation. Rotation redistributes and slows. The object settles, and in settling, it can become less stable than it was in the violence of its birth. This is one of the cruelest patterns in the borderland. A remnant can survive the collision, survive the first scream of collapse, shine, vibrate, radiate, perhaps even launch jets or magnetic outflows, and only later lose the right to remain. The story on the surface is about an explosion or merger. The story underneath is about delayed judgment. Astronomers sometimes classify such objects with names that capture this conditional survival supermassive if they exceed the cold non-rotating limit, but can be supported by uniform rotation, hypermassive if even uniform rotation is not enough, and only differential rotation and heat can postpone collapse. These distinctions sound technical. They are not. They are categories of reprieve. They tell us that the universe allows matter to negotiate with gravity under multiple temporary legal arrangements before the final sentence is carried out. And because each arrangement depends on hidden internal physics, every observed neutron star becomes evidence not just of an object, but of a permission structure. That is why precise mass measurements matter so much. When astronomers find neutron stars around 2 solar masses or more, they are not merely adding entries to a catalogue. They are ruling out equations of state that are too soft to allow such stars to exist. They are forcing matter to reveal how much pressure it can generate before breaking into some deeper form. Radius measurements matter for the same reason. So do merger signals. So do the frequencies of post-merger oscillations. So do X-ray pulse profiles distorted by strong gravity. Each one trims possibilities from the hidden rulebook. Each one tells us where the limit cannot be, even if the exact place is still uncertain. The answer seems clear until the variables become visible. There is no single mass at which all neutron stars become black holes under all conditions. There is a range shaped by composition, temperature, spin, and the still undecided behavior of ultra-dense matter. This makes the borderland more than a threshold. It makes it a diagnostic instrument, because wherever the line ultimately lies, it is telling us not only about gravity, but about what matter is still capable of becoming, before gravity forbids becoming anything at all. And once that is understood, the next step becomes unavoidable. If the limit depends so much on internal composition, then the real mystery is no longer just where the line is. It is what hidden forms of matter inside the core are helping to move it. The deeper the core is imagined, the less adequate the phrase neutron star begins to sound. That name is useful from a distance. It tells us the object is born from collapse, that neutrons dominate much of its interior, that it is denser than any ordinary star and still not a black hole. But usefulness is not the same as truth. The real problem is that a neutron star may cease to be meaningfully describable by the word neutron precisely where its fate is decided. Near the surface, the language still works well enough. There is a crust. There are nuclei electrons, magnetic stresses, perhaps superfluid behavior, developing in deeper layers. But farther down, where density rises beyond what atomic nuclei experience, in normal circumstances, the labels start to fray. Matter is no longer just packed. It is forced into choices no ordinary environment ever demands. And once matter is driven into those choices, the question is no longer what a neutron star is called. The question is, what forms of matter still count as matter resisting collapse at all? The easy picture says the interior is a sea of neutrons all the way down. That picture survives because it is simple, not because it is complete. Real neutron stars may contain neutrons in abundance, but abundance is not the same as exclusivity. Under sufficient pressure, new particles may appear because the system can lower its energy by changing what kinds of matter are present. Protons may persist in smaller fractions. Electrons may remain where charge balance requires them. Muons may appear once the densities and chemical potentials make their existence favorable. Deeper still, the situation becomes more severe. Hyperons particles containing strange quarks may emerge in the core if the pressure is high enough. That sounds like a minor substitution in a technical catalogue. It is not. If hyperons appear, they can change how pressure rises with density, often softening the equation of state and making the star easier to compress. A new particle species becomes a structural weakness. The story on the surface is about exotic matter. The story underneath is about whether exotic matter helps the star endure or quietly undermines it. The same tension applies to one of the most profound possibilities of all deconfined quark matter. In ordinary nuclei, quarks are trapped inside protons and neutrons. They do not roam freely. But in the core of a neutron star, pressure may become so extreme that the boundaries between nucleons begin to lose meaning. Instead of separate neutrons packed shoulder-to-shoulder, matter may pass into a state where quarks move through a shared medium, a dense soup no longer cleanly divided into familiar particles. If that happens, the object remains a neutron star from the outside, yet the core has already crossed into another kind of matter entirely. The name lags behind the physics, and here the uncertainty becomes truly dangerous for explanation because quark matter does not guarantee one outcome. Depending on how it behaves, it may soften the star and lower the maximum mass. Under other assumptions, certain quark phases may generate enough pressure to stiffen the core and help support more weight. The deeper explanation is not that the center contains something exotic. It is that the exotic possibilities move the border. This is why the innermost core matters more than the visible remnant. It is not a curiosity buried at the bottom of the object. It is the constitutional chamber where collapse is either delayed or permitted. Even superfluidity and superconductivity, which can sound almost elegant beside such violence, belong to this same hidden struggle. Neutrons in the interior may pair off into a superfluid state, flowing without ordinary viscosity. Protons may become superconducting, affecting how magnetic flux threads the star. These are not decorative refinements. They change how heat moves, how spin evolves, how sudden glitches happen, how magnetic fields are anchored or rearranged, how the star cools, and how internal stresses migrate from one layer to another. In other words, they change how the object lives out its reprieve. A neutron star is not simply supported once. It is managed from within by phases of matter that alter the terms of survival over time. And the deeper one follows this logic, the stranger the object becomes. A star can look like a neutron star pulse, like a neutron star weigh like a neutron star, and still conceal a core whose contents no ordinary textbook would have predicted with confidence a century ago. It may hold nuclear pasta, at one depth superfluid neutrons below superconducting protons entangled with magnetic fields, then perhaps hyperons or deconfined quarks farther in. The object begins to resemble a layered treaty between competing states of matter, each one stable only under crushing circumstances, each one contributing something to the question of whether a surface can still exist. The answer seems clear until the center is considered. Then the clarity dissolves. Because if the core can change identity while the outer star remains recognizable, the transition to black hole formation is no longer a simple matter of increasing mass. It becomes a matter of which hidden phases appear first, which of them strengthen resistance, which weaken it, and how fast those changes propagate through the remnant. This is why two stars that look similar from afar may not share the same future. One may hide a softer core and sit closer to disaster than its mass alone suggests. Another may carry inner states that briefly hold the line more effectively. And that briefness matters. Because once survival depends on such layered and possibly temporary arrangements, the next revelation follows almost automatically. There are moments when a collapsing remnant may remain alive only because heat rotation and violent internal structure are buying time that matter alone cannot guarantee forever. Collapse does not always finish when it first should. That is one of the strangest mercies in the borderland. A neutron star can be too massive for long-term survival and still remain for a moment or for much longer a neutron star anyway. From the outside, this sounds like a contradiction in bookkeeping, as if nature had made an error and forgotten to close the file. But the real explanation is more severe. The object survives not because the limit has disappeared, but because time itself has become part of the physics. Support can be borrowed. Collapse can be delayed. Judgment can be postponed by conditions that are real, measurable, and temporary. This only looks like stability from a distance. Up close, it is a stay of execution. The easiest place to see this is after a neutron-star merger, when two already extreme objects fall together and create something even less forgiving. These collisions are among the most violent events in the universe outside black hole formation itself. Two compact stars spiral inward over millions or billions of years, bleeding orbital energy into space-time as gravitational waves until the final seconds become a blur of speed curvature and tidal distortion. Then they collide. The surface story says two neutron stars hit merge and make either a bigger neutron star or a black hole. The deeper story is that the remnant may pass through intermediate states where it survives by means that cannot last. The merged core can be grotesquely massive in some cases, above what any cold non-rotating neutron star should be able to support. And yet, it does not always disappear immediately. Why? Because it is born spinning ferociously, heated to immense temperatures and threaded by violent internal motion that redistributes pressure in ways no quiet star ever could. Rotation heat and differential structure combine to hold the object up after matter alone may already have lost the argument. This is not stable support, it is emergency support. A uniformly rotating neutron star can endure more mass than a non-rotating one, because spin helps spread the burden. But a newly merged remnant may be even more extreme than that, with different layers rotating at different speeds. With turbulence, shock-heated material, and magnetic amplification all participating in the struggle. In that state, the object may become what astrophysicists call hypermassive. The term sounds technical. Its meaning is brutal. It describes a remnant that cannot survive indefinitely under any ordinary conditions, but can avoid prompt collapse because violent dynamics are temporarily lending support. The obvious explanation is that the object is still a neutron star. The real explanation is that it is a neutron star only under emergency law, and emergency law expires. Differential rotation redistributes itself. Magnetic fields wind, reconnect, and transport angular momentum outward. Neutrinos carry energy away. Heat radiates and cools. The remnant settles. And as it settles, it can lose the very properties that were keeping the event horizon from forming. The most important thing here is not merely that collapse can be delayed. It is that delay is observable. This borderland does not hide completely in theory. It flashes, it rings, it leaves signatures. A merger that forms a black hole almost instantly may produce one pattern of gravitational wave cutoff, one kind of electromagnetic aftermath, one timescale of jet launching or disk evolution. A remnant that survives for milliseconds, seconds or longer before finally collapsing may produce another. In that difference lies a remarkable possibility. The universe gives us brief experiments in matter at the edge of failure. A delayed collapse is not just dramatic, it is diagnostic. It tells us that the remnant had enough support from some combination of spin heat and internal composition to remain a material object for longer than gravity preferred. That means every moment of survival becomes evidence about the hidden equation of state. Even outside mergers, the same logic appears in slower form. A neutron star can be born from a supernova, rotating rapidly enough to support more mass than it otherwise could. It can live for a long time in that condition, gradually losing rotational energy through magnetic braking and radiation. From the outside, it may look like a successful survivor. Underneath it may be drifting toward a threshold it crossed in principle long ago. The star does not need to gain mass to die. It may only need to lose speed. That is one of the cruelest inversions in compact object physics. What keeps the star alive can also guarantee that death arrives later, because rotation is not a permanent foundation. It is a wasting asset. The achievement is real. The cost is larger. A delayed collapse means nature has found one more way to preserve structure at the edge of black hole formation. But it also means that structure is now dependent on conditions destined to erode. Time itself becomes a pressure term running in reverse. Every second of spin down, every carried away neutrino, every redistribution of angular momentum pushes the remnant closer to a simpler and harsher verdict. This matters because it changes how the boundary between neutron stars and black holes must be imagined. It is not a single crossing that always happens at birth. Sometimes the object is born on the edge and only later slips over it. Sometimes the distinction between neutron star and black hole is not decided by one event, but by the fading of temporary advantages. Matter does not merely resist gravity. It negotiates with it using all available tools, including motion and heat. And when those tools fail, the deeper truth becomes visible. The borderland is not just a place where matter survives. It is a place where survival can be conditional, theatrical, and brief, which is exactly why it lights the universe so brightly when it happens. Because every delayed collapse leaves behind not just a remnant or a black hole, but evidence that the struggle itself can be seen. These objects do not merely survive near the edge of collapse, they illuminate it. That is why the borderland between neutron stars and black holes matters far beyond the stars themselves. If these remnants were silent, compact, and sealed away from observation, they would still be among the most important laboratories in the universe. But they are not silent. They pulse, flare, merge, shatter, bend space-time, and seed the cosmos with matter that will later become planets, technology, and blood. The surface story says, neutron stars are exotic leftovers from stellar death. The larger story is that they are visible pressure points in reality, places where the hidden behavior of matter is forced into the open through violence. And nowhere is that more dramatic than when two neutron stars find each other spiral inward and turn their last moments into a public event. For most of their existence, such binaries live a long, slow sentence. They orbit each other for millions or billions of years, their paths shrinking almost imperceptibly as they radiate energy away in gravitational waves. Those waves are not light. They are distortions in space-time itself, ripples produced by mass in accelerated motion. For ages the system whispers, then the whisper becomes a scream. In the final seconds, the stars circle hundreds of times each minute, then each second until the inward plunge becomes unstoppable. Tidal forces distort them, their crusts strain, their magnetic fields interact. And then the collision arrives, not as a simple impact, but as the sudden collapse of two separate negotiations with gravity into one harsher trial. This is where the borderland becomes visible in multiple languages at once. The merger launches gravitational waves carrying the imprint of mass's spins and deformability. It can eject neutron-rich matter into space. It can produce a short gamma-ray burst if the geometry and conditions are right. It can leave behind an accretion disk, a jet, a temporary remnant, or an immediate black hole. In other words, one event can expose the physics of ultra-dense matter through motion, light time, and aftermath altogether. The obvious explanation is that the spectacle comes from impact energy. The real explanation is that the spectacle is revealing which forms of support failed, which persisted briefly, and what dense matter was able to do before gravity closed the case. This is why events like these transformed astrophysics. The first directly observed neutron star merger, GW 170817, was not only a triumph of instrumentation, it was a new kind of witness. Gravitational wave detectors recorded the inspiral. Telescopes across the spectrum found the electromagnetic counterpart. And within that shared observation was a deeper revelation: the collision had thrown out heavy, neutron-rich material that glowed in a way consistent with freshly forged elements. A kilonova is not just a bright after effect. It is matter reassembling under catastrophic conditions, radioactive decay powering light from debris that has just passed through one of the most violent chemical furnaces in the cosmos. This is where the story widens from compact objects to human consequence. Gold, platinum, and other heavy elements are not ordinary byproducts of calm stellar life. Many of them require environments so saturated with neutrons that nuclei can build upward faster than they can decay. Neutron star mergers provide exactly that. The borderland does not only test matter, it manufactures inheritance. Some of the rarest and most valued atoms in human civilization are born when gravity almost wins twice. First, it crushes massive stars into neutron stars. Then it drives neutron stars together hard enough to rip out their inner material and let it recombine into heavier elements before the final remnant collapses or stabilizes. The achievement is real. The cost is astronomical, but the consequence is intimate. Jewelry, electronics, catalysts, medical technology, traces in ancient rocks and meteorites all may carry the signature of these catastrophes. The universe hides the making of precious matter inside collisions between nearly failed stars. And that is only part of what these mergers tell us. The gravitational wave signal before contact contains information about how easily each neutron star deforms under the pull of the other. That deformability depends on radius and internal stiffness. A puffier star deforms more readily, a more compact one resists. So even before the stars touch, the waveform is already reporting on the equation of state. Then the aftermath adds more clues. Did the remnant collapse immediately? Did it survive briefly? Was the ejector abundant or limited? Was a jet launched successfully? How bright was the kilonova? And how did its colors evolve as heavy elements formed and decayed? Each answer removes possibilities from the hidden rulebook of dense matter. The event is not merely destructive, it is interrogative. It asks matter how much pressure it could make, how fast support failed, and what forms were present at the edge. This is what makes neutron stars so valuable to science. Black holes are profound, but by definition they conceal the interior. Neutron stars stand one step earlier in the process where the interior still influences the outside world in ways we can detect. They are not fully open books, but they are not sealed either. They leak meaning. Through pulses, glitches, bursts, merger waveforms, cooling curves, and elemental debris, they keep telling us how close matter can come to disappearance without crossing into it. And once that is understood, the borderland becomes larger than any single remnant. It becomes part of cosmic history itself. These collisions enrich galaxies. They alter chemical evolution. They give later generations of stars and planets ingredients those earlier generations lacked. The story on the surface is about compact stars dying again. The story underneath is about the universe using extreme collapse to write complexity back into matter. Yet this gift also sharpens the next question. If neutron stars light the universe so clearly when they merge, and if their signals expose the hidden rules of dense matter, then the simplest picture still fails. Because what they reveal is not merely that the boundary exists. They reveal that the boundary is entangled with everything that comes after what elements form, what signals escape, what remnant survives, and whether the final product is still matter with a surface or a black hole where the surface is gone. Gold is not born in peace. That is one of the most revealing consequences of the borderland. Human beings tend to treat valuable matter as though it simply exists, as though the universe presents certain elements fully formed, and civilization later decides which ones to prize. But the real story is harder and more beautiful than that. The heavy elements most associated with rarity, permanence, conductivity, or prestige are not quiet leftovers from ordinary stellar life. Many of them require conditions so violent that even stars cannot make them in their long, stable phases. They need collapse. They need neutron-rich chaos. They need matter driven into a regime where nuclei are no longer assembled slowly by routine fusion, but forced to build upward in a rush before the opportunity disappears. The story on the surface is about chemistry. The story underneath is about a borderland where almost failed stars become factories for the material future of planets and people. Ordinary stars do make elements. That much is true. Hydrogen becomes helium. Helium can become carbon and oxygen. More massive stars climb farther up the ladder, forging heavier nuclei in successive burning stages as they age. But that process runs into a wall. Iron is the turning point. Beyond it, fusion stops paying. The star can no longer earn stability by building heavier nuclei in the same way. So when people hear that stars make the elements, they are hearing a true sentence with an incomplete ending. The real problem is not how to make common matter. The real problem is how to make the rare neutron-heavy elements beyond iron, the ones that require nuclei to absorb neutrons rapidly enough that they can climb into unstable territory before beta decay has time to pull them back. This is the rapid neutron capture process, the R process, and it demands an environment that is not merely hot, but saturated with free neutrons and shaped by explosive dynamics. For a long time, astronomers debated where most of that production happened. Core collapse supernova were long considered likely sites. Some contribution may come from them under the right conditions. But the deeper answer that emerged with growing evidence is that neutron star mergers are among the dominant places where the heaviest R process elements are forged. This should transform how the collision is imagined. A merger is not only the death of two compact remnants, it is a brief opening in which neutron-rich matter is flung outward from one of the most extreme environments in the universe, decompresses, and begins to reassemble. What had been crushed to densities near or beyond those of atomic nuclei is suddenly thrown into space. In that transition, conditions become perfect for a frenzy of nuclear construction. Nuclei absorb neutrons faster than they can stabilize. They climb toward very heavy isotopes. Then, as the debris expands and cools, radioactive decay reshapes that freshly made matter into a distribution of elements that can include gold, platinum, europium, uranium, and much more. The obvious explanation is that the merger makes heavy elements because it is energetic. The real explanation is that it makes them because it liberates matter from an environment already saturated with neutrons, and then lets that matter pass through the exact path of pressure, release, capture, and decay that ordinary stars cannot sustain. The consequence is enormous. It means some of the most prized matter in human life is born not in the stable brilliance of stars, but in their aftermath in a secondary catastrophe, after collapse has already remade them once. A massive star dies and leaves a neutron star. Two such remnants then spend ages spiraling toward each other until gravity forces a second death. Only then does the universe scatter some of the atoms that later become part of planets, oceans, circuitry, medicine, art, and economies. The achievement is real. The cost is nearly absurd. Matter that humans assign the highest value may owe its existence to some of the most destructive events in cosmic history. This is not poetic exaggeration. It is material genealogy. The gold in a ring, the platinum in a catalyst, traces of heavy radioactive elements, locked in ancient rock, all may descend from debris expelled when compact remnants tore themselves open at the edge of black hole formation. And because these mergers are rare compared with ordinary stellar burning, their influence is patchy in time and space. A young galaxy's chemical evolution may depend strongly on how early and how often such events occurred. Some ancient stars show unusual enrichments in heavy R process elements, preserving evidence that their birth clouds had already been seeded by one or a few such catastrophes. In that sense, neutron star mergers do not merely add decoration to cosmic chemistry. They shape the uneven distribution of possibility. Planets forming in one region or epoch may inherit a different heavy element inventory than those forming elsewhere. Technologies available to later civilizations could in principle depend in part on the merger history of their galaxy. The story on the surface is about astrophysical fireworks. The story underneath is about resource allocation on a galactic scale. And yet, even this is not the deepest consequence. Because every heavy element forged in merger ejecta is also evidence that matter survived long enough outside the final remnant to reassemble. The pattern and abundance of those elements encode information about how much material escaped, how neutron-rich it was, how hot the ejecta remained, and whether the merger remnant collapsed immediately or endured long enough to alter the environment around it. The chemistry becomes a witness to the physics of collapse. Heavy elements are not just output, they are testimony. They tell us that the boundary between neutron star and black hole is not an abstract line in theory, but a causal hinge with lasting consequences for what the universe contains afterward. Once that is understood, the next reframe becomes unavoidable. A black hole is not simply the same kind of remnant with more mass, it is a different kind of verdict entirely. Because when the border is finally crossed, the question is no longer which elements will be made or which signals will escape. The question becomes whether matter is still allowed to present any outward structure at all. A black hole is not merely a neutron star that has gained too much weight. That is the tempting simplification, and it misses the real fracture in the story. From far away, the transition can look almost incremental. Add mass, increase compression, push the object over the line. But what changes at that line is not just the degree of collapse. What changes is the meaning of the object itself. A neutron star is still defined by matter. It has a surface, a radius, a crust, an interior magnetic stresses, thermal structure, and hidden phases that shape what the outside world can observe. A black hole is defined differently. Once the border is crossed, the decisive fact is no longer what form of matter is holding the object up, because no form of matter available to the outside universe is holding it up at all. The star has not simply become denser, it has lost the right to remain a star. The easy explanation is that a black hole is what happens when gravity overwhelms pressure. The real explanation is harsher. A black hole forms when gravity does not merely defeat one support mechanism after another, but defeats the existence of any outwardly accessible structure built from matter. That is why the event horizon matters so much. It is not a surface in the ordinary sense. It is not a shell one could land on. It is a boundary in space-time beyond which escape to the outside universe is no longer possible, even in principle, even for light. And that means the object ceases to present the kind of physical identity a neutron star still possesses. Before collapse reaches that point, a neutron star can still pulse, crack, flare, cool, deform, and reveal its internal constitution indirectly through the signals it emits. After the boundary is crossed, those outward signs no longer come from a material surface or a readable interior. They are replaced by a much simpler public face mass spin charge in the cleanest idealization, and the geometry these impose on space-time around them. The story on the surface is about compact remnants. The story underneath is about whether matter is still allowed to define the object from the outside. This is why the difference between neutron stars and black holes is not just a matter of degree. It is a difference in category. A neutron star can be unimaginably dense and still remain an object whose internal microphysics matters to observation. A black hole can form from only somewhat greater mass under the right conditions, and once it does, the outside world no longer has access to the same kind of information. That is what makes the borderland so scientifically precious. It is the last region where ultra-dense matter can still speak. Cross the line and the speech changes into silence, governed by geometry. Even the way light behaves reveals this deeper shift. Near a neutron starlight is bent strongly redshifted and delayed by curved spacetime. Yet photons can still escape from the surface. The star remains visible because there is still a place from which light can leave. Near a black hole, light can orbit, fall inward, or barely escape from regions outside the horizon, but the horizon itself marks the end of outward communication. This is not merely stronger gravity. It is a different relation between the interior and the universe. The obvious explanation is that both objects trap things strongly. The real explanation is that one still permits a material exterior with observable properties, while the other encloses collapse behind a causal boundary. Once that boundary exists, The question of what matter is doing inside becomes more obscure, and in the strictest classical sense, less relevant to outside observation. This is also why black holes seem so strangely simple compared with neutron stars. Neutron stars are messy. They have crusts that can fracture magnetic fields, that can erupt interiors that may glitch, cool, or transition between phases. Black holes, by contrast, strip away complexity from the outside view. However complicated the collapsing matter may have been on its way in the final object, becomes governed by a small set of external parameters. The achievement is real. The cost is total. The universe does not preserve the elaborate internal story in a form the outside can read. It hides it behind a horizon and leaves only curvature behind. That simplicity is not comforting. It is severe. It tells us that there is a point beyond which matter stops being a visible actor and space-time becomes the whole stage. Yet even here the story resists becoming simple. General relativity predicts collapse toward a singularity, a place where known equations cease to behave sensibly. But that prediction is also a sign of theoretical incompleteness. It tells us where current understanding breaks not necessarily what final nature looks like in a full quantum theory of gravity. So the black hole, like the neutron star, still carries a hidden interior question. The difference is that the hidden question no longer reveals itself easily through a surface or emitted structure. A neutron star stands at the edge and leaks clues. A black hole closes the book before we can read the last chapters. That is why the transition matters so much. It is the point where astrophysics changes from studying the most extreme forms of matter to studying the consequences of matter having lost all outward authority. And once that becomes clear, the meaning of the borderland sharpens again. The crucial issue is not simply which objects collapse and which survive. It is that the boundary determines whether the universe remains allowed to inspect matter under ultimate compression, or whether that matter disappears behind a horizon and leaves us only the shadow of its gravity to study. The universe does not let us open a neutron star and look inside. It lets us measure around the edges and infer the rest. That limitation is not a minor inconvenience. It is the central method of the entire field. The decisive physics of the borderland happens in places no instrument can visit, and no laboratory on Earth can reproduce for more than the briefest and most indirect approximations. So the question becomes brutally practical. How do you study matter at densities beyond atomic nuclei? When the object holding that matter is thousands of light years away, only a few tens of kilometers across, and wrapped in gravity intense enough to distort the signals you are trying to read. The answer is that astronomers force the universe to testify through the clues it cannot help leaking. A neutron star may hide its core, but it cannot hide its mass forever. It cannot hide the way its gravity bends light, the way its surface emits X-rays, the way its spin evolves, the way a companion star moves around it, the way it deforms before merger, or the way the merger aftermath shines. Every one of those observables is partial. Together, they become a strategy. The obvious explanation is that scientists are measuring neutron stars directly. The real explanation is that they are reconstructing the hidden constitution of matter from consequences. Consider mass first, because it is both basic and ruthless. When a neutron star sits in a binary system, especially with another compact object, or a closely watched companion, relativity and orbital mechanics can turn the system into a scale. Pulsar timing is especially powerful here. Some neutron stars emit radio beams with such regularity that their pulses become astonishingly precise clocks. As they orbit another object, Those clocks reveal delays, accelerations, relativistic precession, and other signatures that let astronomers infer masses with remarkable accuracy. This is not bookkeeping for its own sake. Every securely measured massive neutron star eliminates equations of state that are too soft to support such an object. A single heavy pulsar can do theoretical violence across an entire landscape of models. It can tell physicists that matter must generate more pressure at high density than some favored theories allow. In that sense, one star can veto entire categories of invisible interiors. Radius is harder and in some ways even more valuable. Mass alone tells us how much burden the star bears. Radius helps tell us how that burden is distributed and how stiff the matter must be to support it. But radii are difficult because neutron stars are tiny, distant, and observed through atmospheres, magnetic fields, accretion flows, and gravitational lensing. X-ray observatories have therefore become part of the front line. Hotspots on rotating neutron stars sweep through view, and the pulse profiles we detect are distorted by the star's strong gravity. Light emitted from the surface is bent, redshifted, and time-delayed. By modeling these effects carefully, astronomers can constrain both the mass and the radius. The result is never a perfect revelation. It is a narrowing of possibility. But that narrowing matters enormously. A larger radius at a given mass suggests a stiffer equation of state. A smaller radius suggests softer matter and less resistance to compression. Once again, observation is functioning like a cross-examination of matter under pressure. Then come the mergers, which add a completely different type of witness. Before two neutron stars collide, they pull on each other tidally. If one is easier to deform, the inspiral waveform changes subtly. Gravitational wave detectors can read those changes. The signal is not just telling us that two compact objects exist. It is reporting on their deformability, and deformability depends on internal structure. A puffier, less tightly bound neutron star leaves one signature. A more compact, stiffer one leaves another. And after the merger, the electromagnetic aftermath adds more evidence. The brightness and color evolution of a kilonova depend on how much material escaped, how neutron-rich it was, and whether a remnant survived long enough to irradiate or alter the ejector. A prompt black hole and a delayed collapse remnant do not leave identical debris histories. In this way, the aftermath of catastrophe becomes an instrument. Even cooling tells a story. Young neutron stars shed heat rapidly at first, and how they cool depends on what particles and phases exist inside. Certain neutrino-emitting processes can drain energy much faster than others. Superfluid transitions affect heat capacity and emission. So when a neutron star is observed cooling in a particular way, it is not just getting dimmer. It is revealing what channels of energy loss its interior allows. Likewise, glitches, sudden jumps in spin rate, point toward interactions between crust and superfluid interior, exposing internal coupling that cannot otherwise be touched. Magnetar flares hint at crustal strain and field evolution. Quasi-periodic oscillations in giant flares may carry information about seismic vibrations and elastic properties. The story on the surface is about different classes of neutron star behavior. The story underneath is that every strange behavior becomes a probe of matter near the edge of black hole formation. This accumulation of indirect methods is what makes the field so disciplined. Scientists are not free to say anything they like about neutron star interiors. Every theory has to survive a tightening net of constraints from timing X-ray modeling cooling mergers and nuclear experiment. Still, the uncertainty remains real. different models can sometimes fit parts of the data. Instrument systematics matter. Interpretation can shift as new events are observed. The answer seems clear until a better measurement arrives. But that is exactly why the borderland remains so fertile. It is one of the few places in the universe where microphysics, relativity, and observation are forced into such close and unforgiving contact. A neutron star is not just an exotic remnant. It is a natural experiment that the cosmos keeps running for us. One pulse, one flare, one merger, one radius constraint at a time. And yet, all of this precision leads to a humbling conclusion. Even with the best instruments, the decisive physics remains partly hidden. Which means the borderland is not only a triumph of measurement, it is also a reminder that some of nature's most important verdicts must still be reconstructed from fragments' shadows and the signals left behind when matter almost ceases to exist. A neutron star does not survive for free. That is the mistake hidden inside the word stable. Stability suggests resolution. A problem-solved a system that has found its resting form and can now simply persist. But a neutron star is not restful in that sense. Even when it endures for millions, billions, or perhaps far longer, it does so under permanent strain. Its survival is not the quiet survival of a stone on the ground or a planet in a settled orbit. It is the survival of an object that has stopped collapse only by entering one of the harshest material states the universe allows, and every part of that arrangement carries a cost. The crust is under stress. The magnetic field can be twisted and buried and re-emerge violently. The spin, if rapid, is a wasting reserve. The interior may be superfluid in ways that make angular momentum shift suddenly instead of smoothly. Heat leaks away. Neutrinos carry energy out. Matter falling in from a companion can rescue the star from one fate while pushing it toward another. The story on the surface is that the neutron star has lived. The story underneath is that living at this boundary means negotiating penalties that never fully end. Begin with spin, because it is one of the most visible forms of borrowed advantage. Many neutron stars are born rotating quickly, and some later become even faster by accreting matter from a companion. This speed can make them seem almost miraculous. Millisecond pulsars spin hundreds of times each second with a precision so great they become cosmic clocks. But a clock can also be a countdown. Rotation is not merely motion layered on top of the star. It is structural assistance. It helps distribute support, and in some stars it may be part of the reason collapse has not yet resumed. That means spin down is not a cosmetic change. It is erosion. Pulsars radiate. Magnetic torques extract angular momentum. Over time, the star slows. Sometimes the slowing is gradual enough to feel abstract. But abstraction is dangerous here. Every bit of rotational energy lost is a reduction in one of the star's defenses. A neutron star may be living off an allowance it cannot replenish forever. The obvious explanation is that slowing down changes the pulse rate. The real explanation is that slowing down can alter the star's survivability itself. Then there is the crust, often described as fantastically strong, and rightly so. It may contain some of the strongest material arrangements in the observable universe. Yet, strength at this level does not mean comfort. It means the crust can endure immense stress before failing, and therefore accumulate immense stress before failing. Magnetic fields can torque it. Spin evolution can strain it. Internal superfluid dynamics can tug against it. When the crust finally yields, the release can appear as glitches, starquakes, or in magnetars eruptions of astonishing intensity. Magnetars are the most dramatic proof that survival is not peace. Their magnetic fields are so extreme that the field itself becomes a source of violence, twisting the crust, injecting energy into the magnetosphere, and occasionally releasing bursts and giant flares powerful enough to be noticed across the galaxy. These are not incidental fireworks. They are signs that the star's continued existence includes chronic structural tension. The achievement is real. The cost is repeated fracture. Cooling adds another layer of penalty. A neutron star is born ferociously hot, but it cannot remain so. It radiates energy away, especially through neutrinos in its youth, then later more through photons from the surface. This cooling is not just a passive slide toward lower temperature. It changes the internal conditions under which matter behaves. Superfluid phases may emerge or evolve. Conductivities shift. Thermal gradients flatten or redistribute. In some cases, rapid cooling may hint at efficient neutrino emission channels opened by particular kinds of matter in the core. So, when a neutron star cools, it is not merely aging. It is surrendering thermal support, reconfiguring internal states, and exposing what forms of matter were present all along. Time once again behaves like an adversary that removes advantages layer by layer. Binary life is no kinder. A neutron star paired with a companion can be spun up by accretion and made visible in new ways through X-rays and bursts. Matter falling onto the surface can trigger thermonuclear flashes. Angular momentum transfer can create extraordinarily fast pulsars. The star can appear rejuvenated. But this is another bargain with hidden terms. Added matter also means added burden. Accretion can push the star toward the very mass limit it is trying to avoid. A process that extends one kind of life can intensify another kind of danger. This is the pattern everywhere in the borderland. Every apparent gain has a shadow. Even the most precise pulsars, the stars that seem almost serene in their regularity, reveal this on closer inspection. Their glitches suggest that the interior is not moving as a single calm body, but as regions coupled imperfectly with superfluid components, storing and releasing angular momentum in abrupt corrections. The star looks smooth until the deeper mechanism becomes visible. And this is what the word survival must finally be made to mean. A neutron star survives because matter has found a way to remain structured under crushing gravity. But remaining structured at that threshold does not mean remaining unchanged, unwounded, or safe. It means existing in a permanent field of consequence. Crusts can crack, magnetic configurations can snap, spins can decay, mass can accumulate, hidden phases can alter the equation of state from within. Some stars may even be drifting toward delayed collapse without announcing the timetable clearly. They are alive, but their aliveness is conditional. They endure, but endurance itself is an expenditure. This is why neutron stars matter philosophically as much as physically. They are not examples of simple resilience. They are examples of resilience under terms so punishing that resilience becomes indistinguishable from managed instability. A neutron star is what it looks like when matter keeps winning just enough to avoid disappearance while paying for that victory continuously. And yet, even after all of this, the most decisive question remains concealed. We can see the penalties. We can measure the timing, the flares, the cooling, the glitches, the merger aftermaths. But the final physics that determines exactly how much can be paid and for how long still happens in a place no telescope can directly enter. The deeper truth is still hidden below the signals, which means the story must descend one step further into what we still cannot see. even after everything the universe has already shown us. The most important physics in a neutron star happens where observation nearly fails. That is the brutal irony at the center of the whole subject. The universe gives us pulsars precise enough to act like clock smudges, loud enough to shake space-time kilonovae, bright enough to expose the making of heavy elements, X-ray hotspots warped by relativistic light bending, and magnetar flares violent enough to crack a crust across the galaxy. It gives us evidence everywhere around the object. But the final verdict about what matter is allowed to become is written in the core, and the core remains almost completely inaccessible. This is not just a practical difficulty. It is a structural fact about the borderland. The place that decides whether a remnant keeps a surface or falls through into black hole formation is buried beneath layers of matter gravity and theoretical uncertainty, so severe that even our best measurements arrive as indirect testimony. The story on the surface is rich with data. The story underneath is still largely inferred from shadows. That should make the field feel weak. Instead, it makes it unusually honest. Because neutron star physics is one of the few sciences forced to admit at nearly every major step exactly how much depends on what cannot yet be seen directly. Consider what we actually want to know. We want to know the equation of state of ultra-dense matter across a range of pressures. No terrestrial experiment can hold for long. We want to know whether hyperons appear in the core, whether quarks deconfine, whether a phase transition happens abruptly or gradually, whether superfluid and superconducting regions overlap in simple layers or tangled geometries, whether exotic matter softens the star enough to lower the maximum mass, or instead creates new ways of bearing weight. We want to know how close massive pulsars are to the edge, whether some remnant classes are only briefly supported by conditions already fading, whether the post-merger object rings in frequencies that betray a particular interior structure, and whether the transition to a black hole proceeds through a clean threshold or through a sequence of failing supports. None of these are decorative details. Each one changes the location of the border. Each one changes the meaning of the object. And yet, none can be inspected by opening the star and looking. The obvious explanation is that better instruments will simply solve the mystery. The real explanation is that better instruments sharpen inference, not access. They do not remove the veil. They force it to become thinner and more precise. Even the best radius measurements rely on atmosphere models, hotspot assumptions, and relativistic ray tracing. Even the cleanest mass measurements tell us only what the support must have achieved, not exactly how it achieved it. Even gravitational wave signals, extraordinary as they are, compress vast physical detail into patterns that must be interpreted through models. The answer seems close until one asks how many unseen choices could still produce a similar signal. That does not make the effort futile. It makes the discipline severe. A neutron star is like a sealed courtroom where the decisive witness cannot appear and the universe must be cross-examined through tremors, light curves, and orbital timing instead. This matters because the uncertainty is not evenly distributed. We know much more about some regions of the problem than others. The crust is difficult, but not utterly alien. Nuclear experiments, many-body theory and observations let us say meaningful things about parts of the outer layers. But the deeper core is where confidence decays fastest, because the densities rise beyond the range where laboratory nuclei and low-density theory can safely guide intuition. Their multiple possibilities crowd together. Hyperons may emerge and soften the pressure. quark matter may appear and either weaken or in some phases partly restore stiffness. Phase transitions may create mixed states or sharp inner boundaries. Transport properties may alter cooling oscillations and magnetic evolution in ways we can only partially disentangle. The deepest layer of the star is therefore not just hidden. It is overdetermined by competing theoretical futures. This is why every new observation matters disproportionately. A single very massive neutron star can eliminate whole families of soft equations of state. A merger waveform with tighter tidal constraints can narrow allowed radii. A post-merger signal one day measured clearly enough could reveal whether the remnant briefly entered a particular oscillatory regime before collapse. Improved X-ray timing can corner the mass-radius relation more tightly. Cooling observations can strengthen or weaken cases for fast neutrino processes. In this field, progress often looks less like revelation than exclusion. We do not yet see the core. We make more and more impossible versions of it. And that narrowing is powerful because reality can hide, but it cannot hide everywhere at once. Still, the deeper philosophical tension remains. We are trying to understand the last visible form of matter before gravity takes visibility away. That means the borderland carries a permanent asymmetry. If matter survives, it can still leak clues. If it fails, a black hole forms, and much of what we wanted to know is suddenly concealed behind a horizon. The universe lets us study the problem most clearly only on the safe side of disappearance. And the safe side is exactly where the answer is hardest to extrapolate from. The achievement is real. The limitation is built in. Neutron stars are not simply difficult objects. They are objects whose greatest importance comes from how narrowly they avoid becoming unreadable. That is why the remaining uncertainty should not be treated as embarrassment. It is part of the meaning. It tells us that nature has placed one of its deepest material questions precisely at the edge where direct knowledge begins to fail. And that leads to the final reframe. The borderland between neutron stars and black holes is not only about stars' collapse or dense matter. It is about a larger rule built into the universe itself, whether reality permits structure memory and outward form to endure under extreme compression, or whether there comes a point where matter is no longer allowed to remain a visible thing at all. The borderland between neutron stars and black holes is where the universe decides whether matter may continue to exist as a visible form. That is the largest meaning hidden inside what first appears to be a technical question about stellar remnants. At the beginning, the story seems to concern dead stars' collapsed cores and extreme densities. But by the end, those are only the outer symbols. The deeper issue is whether structure itself can survive under absolute pressure. A neutron star is not just an object. It is a verdict of conditional permission. It says that gravity may crush matter beyond atoms, beyond chemistry, beyond the ordinary architecture of the world, and still not fully erase its ability to resist. A black hole is the harsher verdict. It says there comes a point where no remaining structure can hold open an outward identity, where matter loses the right to remain legible to the universe beyond it. And once that is understood, the entire story changes scale. We are no longer talking only about what happens after a massive star dies. We are talking about what reality permits when compression approaches its final terms. This is why neutron stars matter so much more than their small size suggests. They are tiny by stellar standards, often no more than 20 or so kilometers across, yet they stand at one of the most consequential thresholds in nature. They are places where matter has already been stripped of almost everything familiar and still manages to hold on. No atom survives intact in the ordinary sense. No chemical bond matters. No comfortable concept of solid or liquid carries over cleanly. And yet the star remains. It still has a surface. It still emits light. It still rotates, cools, glitches, flares, and in some cases merges, and lights the sky with the creation of new elements. The obvious explanation is that it survives because pressure balances gravity. The real explanation is larger. It survives because the universe still allows matter in some hidden and punishing arrangement to preserve form against the strongest collapse short of a horizon. That makes every neutron star a demonstration of a profound fact structure, is more durable than ordinary intuition suggests, but not infinitely durable. There is a last defensible shape of matter. Somewhere beyond it, defense ends. This is why the transition to a black hole cannot be reduced to a difference in amount. It is a difference in kind. A neutron star still belongs to the world of material objects. A black hole belongs to a world where geometry overtakes material description. On one side of the line, the interior matters because it still influences what the outside can observe. On the other side, the outside world is cut off from that interior by the existence of the horizon itself. One side leaks clues through pulses, waves, temperatures, and elemental debris. The other presents a stripped public face and withholds the rest. The story on the surface is about compact remnants. The story underneath is about whether reality is still willing to let matter speak. And that is why the borderland has consequences far beyond astrophysics. Heavy elements are forged there. Signals used to test relativity and nuclear theory are born there. Whole categories of astronomical observation take their meaning from there. Even human existence is touched by it, because matter expelled from these nearly terminal events becomes part of later stars, later planets, later chemistry, later life. Gold, platinum, uranium, and countless other heavy nuclei may owe their existence to this exact threshold to matter, surviving just long enough under collapse to be torn free and reassembled elsewhere. The achievement is real. The cost is cosmic. The universe writes some of its richest material complexity at the edge of disappearance. Yet the greatest significance of the borderland is still philosophical as much as physical. It reveals that collapse is not a simple on or off event. It is a negotiation with layers. First, ordinary stellar pressure fails. Then, atomic structure fails. Then, nuclei are pushed toward breakdown. Then, deeper forms of pressure, degeneracy, nuclear repulsion, perhaps superfluidity, perhaps quark phases, perhaps other states not yet fully understood, rise to answer gravity in turn. A neutron star is what it looks like when the universe keeps finding one more layer of resistance. A black hole is what it looks like when the layers run out. That is the final synthesis of the entire story. A neutron star is not just a remnant of death. It is matter at the last moment before matter ceases to define the object. It is a pause, yes, but not an empty one. It is a meaningful pause, one in which the laws of nature reveal how far they are willing to let structure endure. And that is why these stars remain so compelling. They are not merely exotic, they are judicial. In them, gravity presses its case as hard as it can without immediately erasing the evidence. In them, matter answers with the deepest resistance it possesses. Sometimes that answer is enough for ages, sometimes only for moments, sometimes not at all. But every time the same question is being asked beneath the spectacle: how much can reality compress a thing before that thing is no longer allowed to remain itself, In the borderland between neutron stars and black holes, the universe gives its answer, not in words, but in pressure, light collapse and survival. What begins as the death of a star ends as a question about the endurance of form itself. That is the final scale of the borderland. A neutron star is not merely the corpse of stellar collapse. It is the last visible proof that matter can still organize, still resist, still hold a surface against forces that have already erased almost everything familiar. A black hole is the point beyond that proof, where resistance no longer survives in any outwardly readable way, and space-time takes over the story. This is why the border matters so much. Not because it separates two exotic astronomical objects, but because it reveals a deeper rule about the universe. Reality does not surrender structure easily. It strips away the easy forms first. Fusion fails. Atoms fail. Ordinary matter fails. And still for a while, something deeper answers back. Degeneracy, nuclear forces, hidden phases. Extreme states not found anywhere in ordinary life all rise in sequence, as if the universe is testing how many layers of resistance existence can contain. A neutron star is the last successful answer. A black hole is what follows when no answer remains. And yet, the story does not end in loss alone. From this threshold come some of the heaviest elements in the cosmos. From this threshold come the signals that let us test gravity matter and the limits of theory. From this threshold come pieces of the material inheritance that later build worlds, machines, and living things. The universe places some of its greatest acts of creation exactly where collapse is closest to becoming absolute. So the borderland between neutron stars and black holes is not only a frontier of astrophysics, it is a frontier of meaning. It is where the cosmos shows with unusual clarity that existence is not defined only by what is born, but by what can keep its structure under pressure almost beyond permission.